Hello students, welcome back. We're just through a confidence interval and confidence bound problem for binomial proportions. Now let's consider a sample size problem. Please stop the playback and read through. So what do we have here? Basically, this problem is visualized like this. Well, lousy picture, but let's suppose this is normal. And what is the best point estimate? Oh, we don't know that. What are the endpoints of the confidence interval? We don't know those either. What do we know? Well, 97% in the middle, and then consequently, the other 3% I'm going to be wrong, so over here, 1.5%, and 1.5% there. Okay, there you go. Looks like there are too many question marks. How can we do this? But as a matter of fact, it's going to be okay if you change the viewpoint a little bit. So what is the z-score formula? Z-score formula is like this. So end minus center over SE. And this looks pretty bad because we know neither the end nor the center. But then again, end minus center, actually we do know. Margin of error is 2.0%. So this distance here, that's 2%. So E minus C is 2% point. So this is actually 2% point, 0.02 over SE. And that's the z-score associated to this 1.5% there. If you look up the z-table, you're going to get 2.17. So that is the structure of this problem. Not completely done yet, but at least this is how you can start. All right, let's get out of this lousy picture and let's go to a little bit better visualization here. Okay, there you go. We don't know the center, the point estimate, but we know the margin of error. This plus 0.02 to get there, this minus 0.02 to get there. So what do we have here? In the end, z-score is n minus center over SE. Let me expand the font. Sorry, wrong key. Is margin of error over P1 minus P over N. And margin of error in this case is 2% point, isn't it? And that has to be approximately equal to the z-score associated to 97% in the middle, so 1.5% here, 1.5% there. Let's look up the table. Do we actually have 2.17 as I said before? Well, let's see. Here, left-hand side, 1.5%. right here. 1.5% is here, as this is negative 2.17. But that's to the left, so to the right, I want positive 2.17. So yes, all checks out. So 2.17. From here, what is n? That's the question. Can you solve this? No, not really, because n value, yes, that's unknown. But what about p? If I know p, plug those in, and everything other than n is known, so we can solve for n. But for now, it's impossible. Is there any way to handle it? The answer is yes, there is. If the problem explicitly gives you p-value, that is, the proportion is expected to be around, say, 3.5%, 35%, so 0.35, put it in there, or 76.2%, 0.762, put it in there, you can do it. But if there's nothing there, then as a default, you use p equals to 0.5, 50%. Use p as 50%. Why 50%, you may wonder? Well, we want an underestimation of n, at least by how much? So we want largest possible error, but still it is negated by we want largest possible error, but still it is negated by sufficiently large sample size. Now, what is the maximum error? Is it really 1/2? Well, look at this expression, p1 minus p. That's quadratic expression, isn't it? If you plot this graph, x1 minus x, this expression, p1 minus p, this expression, the numerator, you get this parabola because it's a quadratic function. Maximum takes place at the vertex x equals 1/2. So that is the maximum. So that's what you plug in place of p. Not just anything, but 0.5 here. If the problem gives you appropriate p-value to plug in, then you can use that. But if it doesn't, then always plug in p equals to 0.5. The reason I just showed you. The numerator is a quadratic expression, and that takes the maximum at p equals to 0.5. Now we have this equation. This is a benign equation. You can solve it algebraically. This is 3000 level course, so solving this equation algebraically should not be too much of a problem here. I mean, isolate this square root, flip it to the right hand side and divide it, and then square both sides to remove the square root, and go ahead algebraic solving. Yeah, like that. So SE, this is square root expression, is margin of error over the z-score, and then square both sides. And then so for n, you end up with 2,943. So, I'd prefer to have about 3,000 people after reasonable rounding up. And that's for math classroom purpose only, as a matter of fact. In reality, you need significantly more than 3,000 people because you have to count in non-responders. But that depends heavily upon what kind of demographic, what kind of previous records, what kind of history you have, and that's not really a mathematical part. The math part stops here, and it stops at about 3,000 people. All right, that was the last example of section 2, and let's say we are done with section 2. We'll talk about section 3 in a separate video.